Buckypaper is a thin sheet made from an aggregate of carbon nanotubes or carbon nanotube grid paper. The nanotubes are approximately 50,000 times thinner than a human hair. Originally, it was fabricated as a way to handle carbon nanotubes, but it is also being studied and developed into applications by several research groups, showing promise as vehicle armor, personal armor, and next-generation electronics and displays. Background: Buckypaper is a macroscopic aggregate of carbon nanotubes, or buckytubes. It owes its name to the Buckminster fullerene, the 6D-carbon fullerene. Synthesis: the generally accepted methods of making CNT films involves the use of non-ionic surfactants, such as Triton X100 and sodium lauryl sulfate, which improves their dispersibility in aqueous solution. These suspensions can then be membrane filtered under positive or negative pressure to yield uniform films. The van der Waals forces interaction between the nanotube surface and the surfactant can often be mechanically strong and quite stable, and therefore there are no assurances that all the surfactant is removed from the CNT film after formation. Washing with methanol, an effective solvent in the removal of Triton X, was found to cause cracking and deformation of the film. It has also been found that Triton X can lead to cell lysis and in turn tissue inflammatory responses even at low concentrations. In order to avoid adverse side effects from the possible presence of surfactants, an alternative casting process can be used involving a frit compression method that did not require the use of surfactants or surface modification. The dimensions can be controlled through the size of the syringe housing and through the mass of carbon nanotubes added. Their thicknesses are typically much larger than surfactant cast Buckypaper and have been synthesized from 120 I1/4 m up to 650 I1/4 m. Whilst no nomenclature system exists to govern thicknesses for samples to be classified as paper, samples with thicknesses greater than 500 I1/4 m are referred to as buckydiscs. The frit compression method allows rapid casting of Buckypaper and buckydiscs with recovery of the casting solvent and control over the 2D and 3D geometry. Aligned multi-walled carbon nanotube growth has been used in CNT film synthesis through the domino effect. In this process, forests of MWNTs are pushed flat in a single direction, compressing their vertical orientation into the horizontal plane, which results in the formation of high-purity Buckypaper with no further purification or treatment required. By comparison, when a Buckypaper sample was formed from the 1-ton compression of chemical vapor deposition-generated MWNT powder, any application of a solvent led to the immediate swelling of the film till it reverted into particulate matter. It appears that for the CNT powder used, compression alone was insufficient to generate robust Buckypaper and highlights that the aligned growth methodology generates in situ tube-tube interactions not found in CVD CNT powder and are preserved through to the domino-pushing formation of Buckypaper. Properties: Buckypaper is 1/10 the weight yet potentially 500 times stronger than steel when its sheets are stacked to form a composite. It could disperse heat like brass or steel, and it could conduct electricity like copper or silicon. Rice University scientist Wade Adams says, "All those things are what a lot of people in nanotechnology have been working toward as sort of holy grails." Applications: among the possible uses for Buckypaper that are being researched, fire protection. Covering material with a thin layer of Buckypaper significantly improves its fire resistance due to the efficient reflection of heat by the dense, compact layer of carbon nanotubes or carbon fibers. If exposed to an electric charge, Buckypaper could be used to illuminate computer and television screens. It could be more energy efficient, lighter, and could allow for a more uniform level of brightness than current cathode ray tube and liquid crystal display technology. Since individual carbon nanotubes are one of the most thermally conductive materials known, Buckypaper lends itself to the development of heat sinks that would allow computers and other electronic equipment to disperse heat more efficiently than is currently possible. This, in turn, could lead to even greater advances in electronic miniaturization. Films also could protect electronic circuits and devices within airplanes from electromagnetic interference, which can damage equipment and alter settings. Similarly, such films could allow military aircraft to shield their electromagnetic signatures, which can be detected via radar. Buckypaper could act as a filter membrane to trap microparticles in air or fluid. Because the nanotubes in Buckypaper are insoluble and can be functionalized with a variety of functional groups, they can selectively remove compounds or can act as a sensor. Produced in high enough quantities and at an economically viable price, Buckypaper composites could serve as an effective armor plating. Buckypaper can be used to grow biological tissue, such as nerve cells. Buckypaper can be electrified or functionalized to encourage growth of specific types of cells. The Poisson's ratio for carbon nanotube Buckypaper can be controlled and has exhibited oetic behavior, capable of use as artificial muscles. See also, frit compression, carbon nanotube, graphene oxide paper, potential applications of carbon nanotubes, graphene. References. External links. FSU researchers Buckypaper is stronger than steel at a fraction of the weight. Research and reviews. Buckypaper are nanotubes on steroids. Pictures of Buckypaper and an interview with Frank Allen, Operations Director of the High Performance Materials Institute at Florida State University.